Hey everyone, my name is Pete Sacco. This was a presentation that I did at AFCOM's Data Center World back on April 17th in Washington, D.C. It went pretty well, so I thought I would record it because a lot of people asked for it, and we didn't record it at AFCOM. So the presentation is defined or called Build Sustainability. It was part of the Data Center Build conference, and it's a construction design for a generatorless future. So first of all, I think we all need to be in agreement that AI is going to be the most transformational technology ever. It is going to be akin to electricity, akin to water. I would actually argue that we are not going to recognize the world. We'll begin to not recognize the world in 10 years, but in 20 years, we're going to live in a completely different world. So let's start off of how I came up with that. And so PTS, the underlying company that owns the three brands, Intuva, Grid 7, and Inspirica, I'm the founder and CEO and president of these companies. And we've been designing and building data centers and around IT and cybersecurity and now microgrids for over 20 years. And so there's a lot. At the end, I'll put some links to it. If you could give me a call, reach out to me on LinkedIn, and I'd be happy to talk to you about it. So everything starts with me with a purpose. And mine is to inspire and accelerate mankind's transformation to a world of transparency, information transparency, and trust. I believe what that's going to look like is decentralized technologies and open AI, not just AI, but open AI, blockchain, tokenization, and most of all, digital assets and digital security. And of course, I'm going to do that, as you saw from the tagline of the technologist mystic. I'm going to do that while living a balanced existence of mind, body, and spirit. So the first thing I'd like to run through is a couple lessons learned over the years. And in 20 years, you learn a lot. And the first one, this is a story that happened early on in my career where I got to assess a data center in Korea, of all places, for a very large conglomerate. And they asked me to evaluate that data center, and it was scathing. There was a lot of problems, and it was almost 15 years to the day, well after I had a relationship with them, that a fire ensued and destroyed a good portion of the building, exactly where I said it would happen and I said it would happen. And so the lesson learned is defend your principles even when they're unpopular. By the way, that client fired me because of my scathing report. Didn't fire me, paid me, asked me never to return. Same thing. But again, stick to your principles. You know, like Al Gore, who invented the internet, I like to say that I invented ducted return cooling, and I say that tongue in cheek because a lot of people had the opinion at the same time. But the lesson learned is don't be afraid to go against the status quo. And here's the story. So there was a large, the company was called DataPipe at the time, and they were operating in a co-location center, and the co-location provider couldn't get the cooling for the rack densities that they were looking for. And so I came up with ducting their heat up into the drop ceiling and then actually putting grates over the top of their air conditioners with the permission of the suite they were in with the operator. It worked really well. Well, and when they moved out of there and we designed and built their first data center in New Jersey, they wanted me to build this into it. Well, unfortunately, at the time, this was many, many years ago, all of this was very much vague in the code and actually probably against the code. And so I was reluctant to do it on a grand scheme. Well, as clients would have, they basically found a mechanical contractor that would do it anyway. And you know what they say, the rest is history. They did it and quite successfully. And not very long after that, it became a thing. So don't be afraid to go against the status quo. So, how does it relate today? Well, my answer is it's not going to happen this time. And so, because I understand when I was 30 years old and I started PTS, that's way different than today at 56 years old. And I know where the data center industry is going. And the reason for the funny little picture is that for AI to be fully realized, there doesn't need to be a few more data centers. There needs to be a lot more data centers, and they're going to be everywhere. So the big question is, what type of data centers? And the answer is all of them. You see, when the circus tent goes up, all parts of the tent rise with it. And so if we take a look at the data center industry as being the hyperscalers in the centralized regions, let's call them the American pro football cities of the world, right? And then the middle of the tent is the managed service and managed hosting providers. And let's say that they are in the NCAA college football cities of America. By the way, I coached football for many years too, and so that's everything's going to be a football connotation here. And so, if we take a look at the ever burgeoning edge that's been predicted to grow, well, with the rise of AI, that's where we're going to see that edge of the tent rise. So when the tent goes up, all of them are going to go. All right, so how about we take a pause and a history of the data center, and really it can be explained in one slide. In the beginning, there was centralized data centers. It was hardware centric, it was mainframe centric, and it was really dominated by IBM. And then that gave way to the decentralized model of software, where hardware became, um, you know, open and decentralized. And that gave way to where we find ourselves at the end of the cloud era, where funny little thing happened on the way. The product became us. We gave away our data and our trust on all of the cloud era platforms. And that solved a lot of the problems for the Googles and the AWSs and the such. I believe that that's going to give away to the decentralized era. Now, this was a stock from Muniba Ali from Blockstack. But I think it's very pertinent because we're going to move into that decentralized era where there are no data monopolies and where data is used and owned, across a decentralized spectrum. And I believe the data center will follow track. And so, what does the data center industry look today? Well, the enterprise data center today is massively complex. And so, here's a slide from Gartner, and I thought it really captured it well, right? Because you're talking about data center, and here it just says data center, but let's think primary and secondary. These could be edge or these could be co-location. But then you mix in, all of your platform as a service and software as a service and infrastructure as a service for private cloud. Then you have all of your edge locations and branch locations and device edge locations, and it makes for a very complex. The data center is no longer limited by walls. And so, what has been AI's impact on the data center? I would argue that the AI industry caught most of the support infrastructure vendors completely off guard. I mean, you at the Data Center World Show, it seemed like every other vendor was a liquid cooling provider that was providing direct to chip or rear door heat exchanger or direct to cold plate, because GPU loads are super high density and they're demanding huge amounts of power. And so those are common. What was interesting is the diversity of the amount of suppliers doing it. It wasn't just the Schneider Electrics and the Vertivs and the big guys. It was actually a whole bunch of small guys, because I think the AI industry caught everybody off guard. And if you think about it, we weren't even talking Chat GPT 2 years ago. But now, so the AI impact on power is, I would argue the US isn't running out of power, but we are lacking transmission and energy storage, because the problem is the power. Remember what I said about the hyperscale data centers? They're highly centralized, right? And they sit in the American pro football cities, and it's the American pro football cities that are running out of power. If you get out to the edge of America, there's plenty power, lack of transmission and energy storage. And so I think that is just one thing that will continue to drive, and that's going to change the energy landscape. So how about the data center market itself? Well, here's a Gartner paper, and this one's projecting 21 all the way through 2027. If you'll find in North America, I know it's an eye chart, but if you go from single rack data centers all the way through large data centers, you know one thing in common. When the circus tent goes up, they're all going up. And look, I got it. It's a prediction. And you know what? We plan and God smiles, right? So we don't really know what the prediction is, but I'm going to venture to say that in the AI world, we are going to see a massive increase in the building of data centers. Okay, so are we seeing any trends of decentralization? I think the obvious one is currencies, right? Love them or hate them, Bitcoin and all the altcoins are here to stay. I'm a big proponent, by the way. Do yourself a favor and invest in Bitcoin, because even at this levels, just by massive supply and demand, it's going to grow immeasurably. But the decentralization trend is in. So here's a correlation between Bitcoin and S&P, and you'll notice up through 2019, just prior to COVID, there was a highly decentralized correlation, high decorrelation between the S&P and Bitcoin. Closer to zero, decorrelated, higher or closer to one, correlated. Now, in 2020, when money became free because of the federal government and PPA, PPP, you basically saw a greater correlation, but you actually saw a correlation between all asset classes because money was in the streets and everybody was doing nothing. Now you're seeing as that money is drying up, you're seeing that decorrelation continue. And so I would argue that the currencies were first of the decentralization trends. A second one would be in the distributed workforce. I mean, here's some stats from Forbes and other places that the majority of Americans want to work remote at least some of the time. And we've learned that we can do that. I mean, my own very companies, half of my employees work remotely and or on some sort of a flex schedule. And I'm starting to hire people from other places of the country. In critical, it opens up the marketplace as to who I could actually have. I'm hiring for culture and expertise more than I'm altering for locality. A third trend is power. Is another eye chart, but energy is becoming distributed. I'll draw your attention to the third one. How about AWS purchasing Talon Energy to put a Texas-based electric generation nuclear power plant? I believe it's Pennsylvania, but it could be wrong there. But purchasing, what does it mean when a hyperscaler is buying a nuclear power plant to meet their energy demands? But it's full of stats about people. Microgridding is becoming, a thing because it's my argument that you're in that centralized region where we can't build more power fast enough. We're going to use microgrids to deliver power. We're going to, in the region that you are, will deliver power that is available. Okay, so is the data center at an inflection point? Well, it's got power challenges, and there's definitely a decentralization trend. We have an unexpected AI impact that's only going to grow. In fact, I would argue that in the grand scheme of things, if AI was a clock, a 24-hour clock, we're only at 1 and 2 o'clock. Before it's fully realized, before artificial general intelligence and superhuman intelligence, which is inevitable in my opinion. I know that's maybe a bit presumptuous, but it is, I believe it to be so. And so the AI's impact is going to be enormous. We are seeing finally a sustainability focus. I still think that availability trumps sustainability for most and cost above all. But regulatory compliance is obviously becoming with data protection laws and data sovereignty is becoming an important part of it. So I do believe the data center industry is at an inflection point. And so what does the future of it look like? Well, the hybrid model is here to stay. We're going to see the idea of edge data centers in play with co-location and managed hosting and all the Gartner pictures that you saw there. So the hybrid model is here to stay. Sustainable operations is inevitable. AI and automation are only going to get bigger, and regulatory agility is going to have to be required. We're already seeing innovative cooling and energy solutions from liquid and immersion and other cooling methods and power, to which I'm going to talk about ways to be able to do that and enhance that. And then advanced computing integration. I would argue, and again, I'm going to challenge the status quo to say that GPU-based technologies are not going to be the only technology that carries us into the AI age. I would argue that its liquid cooling, its massive energy consumption is unsustainable. And I personally invest in a number of startup chip manufacturers that I believe are going to turn silicon-based solutions into lower power at much greater compute capacity than GPUs. Remember, compute is either for sequential processing, it's CPUs. At the other end of the spectrum, you have FPGAs for parallel processing, who do that superior. And then in the middle, you have GPUs that are today the favorite. I believe the first one you're going to see is cards that actually share CPU, GPU, and FPGAs on the same card, and then use software to dynamically switch the workloads to the algorithm, to the compute center that it actually works best. And they're going to operate at a much better energy consumption model than stuffing everything into one broad spectrum type. And then, of course, we'll see advanced security types. All right, so what does that data center, if we are going to see a distribution to the edge, what could a data center look like? And so here, this is my concept of my data center facility reimagined. And let's give you a couple landmarks here. And so what you're looking at over here are indeed linear generators. So the approach here is, this was my aha moment that I was referring to back when I said not this time. And so you're looking at what I like to refer to is a distributed edge, or more appropriately, a near edge data center. I believe, following with my football theme, they're going to be vastly distributed in the high school cities. They're going to be smaller and modular and high density and high performing, and yes, generatorless. And it's not lost on me that I'm saying generatorless, and this is a linear generator, but it's not a standby generator in the sense of it's sitting there idle until I hopefully never need it, but need to use it. That's an awful lot of money that goes into it. I believe as AI becomes real time, meaning the learning models that we do that are not going to be fixed point in time of learn on my data from this date to this date, but more appropriately, learn every day that real new data is put on there. Those AI workloads are going to be closer to the edge. And when they are closer to the edge, they are going to be in a vastly distributed array of data centers that are at the high school footballs, the tertiary cities of the world, if you will. So some landmarks. This is a linear generator. It is the primary energy source. It is hydrogen power packed. It creates electric at the edge. Then there is, yes, a utility, and it runs through a single UPS. And no, you do not see a standby generator. And in this room are the static switches and automatic transfer switches and distribution, combining the energy that is created by the linear generators and parallel with the power coming from the electric grid, and then feeding it through here. And then so that the building, and this is a 1 megawatt suite and a second 1 megawatt suite with a common area. And what you're seeing here are the air conditioners sitting external to the building. This happens to use an indirect evaporative cooling approach. And so there's no infrastructure inside the building. I'm going to tip to the nod to the hyperscalers who are building massive facilities with modular construction outside every day, but it can be done for roughly the same price at much, much smaller scale. And so this is a 50 kilowatt per rack cooling design, and it's very adaptable. You're going to see as we go on, I can make it look like anything. And so let's go back and let's talk about the future of the data center industry. So again, to Gartner at their picture, I thought this captured it well. Let's talk the top one, cloud. That's the distributed cloud and that ecosystem of integration. And then you have all of the data center industries, the content delivery networks, the telecom, the telecom data center, the co-location providers, the managed hosting providers, which again are in that regional, that NCAA city, not just the primary American pro football cities, but that larger. And then we have the edge, and the edge goes everything from that small data center, the micro data center, it could be their primary data center, but still at the vast majority of them are still owned by the enterprise, and the government and institutions. Yes, they're all migrating to co-location and the cloud, but the edge is still a thing. Went all the way down through the compute edge and the gateway edge, and eventually where AI is going to sit in that device edge. But I believe, again, as AI becomes real time, there's going to be a new layer, and that's the distributed edge. And I actually have been changing it to the near edge because Gartner tells me they've got a hook on the name distributed edge. So I'm going to change it to the near edge data center. And so here's what it might look like. And it's the two green ones in the middle. And the top green one says the distributed edge data center. So I think that's an enterprise near edge data aggregation shared facility in the tertiary cities of the world. So in other words, all of your AI real-time devices need to federate. And so that data is going to go to a near edge data center where it's federated with all the near edge devices. That information gets passed up to a regional data center where it is combined with, say, the organization's all of the learning federated from all of the devices nationally. And then the deep learning might be done in the cloud for inspection. And then the inferencing goes all the way back down to the edge for implementation of that learning. And so, but in order to do that, you need that near edge data center arranged. I think a second way to do that would be what I call the outsourced edge data center, and that's that enterprise non-owned data center. So for instance, I'm working with New Jersey University right now that's weighing the option about building a micro edge, and I'm working with a large managed services provider to potentially build a much larger data center on their campus, and then they would become the main tenant for that, but it's on school property, on campus property. And then so this would be that outsourced edge data center. They would be the primary tenant, but it would open it up for us to operate it as a co-location and more prevalently a managed hosting site, but on the customer's property. I'd argue that another play in that model is eventually going to be that it won't be owned by a very large colocation operator. I believe it's possible that the distributed data center future industry might be DAO-like, distributed autonomous organization, where it's actually not owned by one singular government or large enterprise, but it actually will be an amalgam of a lot of different owners all sharing on as a node to the collective. I know that sounds very Star Trek-like, very Borg-like, but is there any other place that we could point to where a DAO works pretty well? How about Bitcoin? Bitcoin is the perfect example of it, where every miner is contributing to the transaction computing of that, and they work, and you get rewarded by your level of compute. I think a DAO-based distributed network of near-edge data centers would work very much the same way. And so what would potentially, so what did I use as a strategy? Excuse me, I lost myself for a second. So I needed a balanced approach that was going to reduce complexity, minimize the CapEx and OpEx, and make it a very workload-centric strategy, since that's been changing the data center so much by what the workload is. And so my goals were, it needed to cost less to build and operate. I needed to be able to deploy faster, and generators are a weak link because they're 24-month lead times right now, and it needs to perform better. You know, a lot of the data centers that are out there are 20 years old. Tell me, because I'm doing a lot of work for data center operators right now of improving their facilities, their chiller operation, and how do I extend the life of the chiller, because I need to get more chilled water at different temperatures working. Reach out to me. I've got a great solution, by the way. If you're a data center operator and need to extend the life of your chiller system, I've got a great way to do it. And so my approach was to design quickly, build fast, make it energy efficient, and use modularity for riskless expandability. And so here you're seeing two options. On the one on the left, you're seeing the linear generator option that you saw before. You're only seeing it built out in a 1 megawatt approach right now. And the one on the right is actually using a solid state fuel cell. And so that's the approach. You could use both. I kind of leaning towards the linear generator option lately. It doesn't have some of the intrinsic problems that the solid state fuel, but I want to tip a nod to the solid state fuel industry. Both of these technologies, by the way, are kind of like the oldest new technologies that are out there. I mean, they're being newly used in the data center industry in a new way. But truthfully, the technologies are long out and long proven. And if it's not clear, you're noticing that everything is built here on this 1 megawatt chunk. But the truth is, this whole property is less than 2 acres, right? And that's on both sides. And so on less than 2 acres, I could achieve 2 megawatts, and it's highly modular. So if you want to turn this to a second floor, great. Expand to double the outside space, which you're noticing there's about a 2-to-1 relationship between the outside to the inside. But you could make this facility any level of power that you want, as long as you have enough space to do so, and the price scales with that. And you're going to see later on, I'm going to talk about price, and it actually scales pretty well with the amount of infrastructure that you want to support. Here's just some other pictures, and so what does it mean generatorless anyway, right? You know, again, I'm not using that traditional standby data center, and you're only limited by the amount of land that you have. But here is, a diagram. And so again, this whole building for 2 megawatts is only 11,700 square feet. The whole property is 1.75 acres. And here you could see again the linear generators, and here you're seeing your UPS. These are your static switches and distribution. That's your utility transformer, and then you have your racks inside. The room is really only used for air distribution and low voltage cabling. I'm keeping everything possible out of this room as possible, even the air conditioning system here that I'm using, and we're going to talk about the iDeck later, is basically there's nothing inside the room, and each one of these is a standalone system. By the way, I can modify this for whatever cooling concept you want, a combination of air cooling and liquid cooling, including rear door heat exchangers and cold plate and direct to chip and immersion cooling and every variation that I'm designing today therein. So this is what the block diagram looks like. And so what you have from a reliability standpoint, it's really difficult to beat the reliability here. But I do want to point out a couple things. First of all, the natural gas utility is running through the linear generators, and you'll note it's running not just the critical load through the A side of the static switches, but it's also running through transfer switches, the building loads and all the mechanical loads. And the electric utility and its non-redundant UPS is actually the B side, and it's on standby. And so we're actually we'll actually utilize this through the linear generators. And by the way, it's not a hard and fast. The UPS could be half on and half on through the linear generators as well, so that you're operating. If you wanted to get rid of the static switches, you could do that. But again, I think the approach here is very good. But let's just talk about it. So the linear generators are 250 kilowatts a piece, right? And I connected these, you're going to see in the next slide, in a 5+2 arrangement for the critical load. So to achieve 1100 kilowatts per suite. And if you do the calculations of expected uptime, it's 99.87%. You would say, Pete, that's not high enough. Well, let's finish. So let's say now a typical North American electric utility with a non-redundant UPS per megawatt suite has an expected annual uptime of 99.67%. And that's slightly worse than the linear generators. But remember now, we're using them in tandem across a distributed array of static switches. And so if I put that together, I really truly have what Uptime Institute, defined as a tier 4 system. And if you put the two together, two disparate energy sources from two disparate systems feeding through the static switch, the uptime annually is calculated at 99.999957%, or 2.26 minutes per year. And I would argue at less money, I'm actually achieving greater levels of resilience. And so here's what the one-line diagram looks like. I know it's an eye chart. We won't stay on it too long. But the point is that the power to the mechanical and the base loads are also serviced by both energy sources, as well as the critical load. And yes, I typically do put an optional roll-up generator connection in there, as the belt plus the suspenders at the same time. But again, they're completely flexible facilities. So I know everybody wants to see this slide, is the CapEx and OpEx considerations. And so here's what you're looking at. That building cost about $16.7 million from a CapEx for a 1 megawatt build. It is scalable to 2. And your breakdown, 78% is in construction, 11% general conditions, 6% design, 5% contingency is built into that. And core and shell of that was 4.8 million. And I'm not going to read them, but you could see the costs per building and the cost per square foot, the cost for the fit out. But the real slug right there, the data center hall and support infrastructure, $15 million build, right? And so assuming you're building both suites out at the same time, the most critical number, that critical load of about $10,000 per kilowatt, of the critical load, which scales with the size very linearly, because that's how, and by the way, this is at very small. So at scale, we're going to reduce that even further to compete with what we're doing, that $8 million a megawatt, and trying to get that even lower. That's typically done with a traditional design, but at much larger scale, at 20, 40, 60 megawatts before you can actually achieve those kinds of numbers. And you have to have the purchasing power of the most elite data center operators in the world. I would argue that the annual operating cost for this is a bit lower than the traditional data center, and that is including all facets of it, the cost of the gas, the cost of the electric, and the maintenance, and all of the other things. There'll be further dive on this. So why the linear generator? So the linear generator is selected, and this is a real site. That's a 25 megawatt site. It's fuel flexible. And by the way, I'd argue that as opposed to the solid state fuel cell, which really needs hydrogen, so we have to do a lot to the natural gas to do it. The linear generators are very fuel flexible. I could pump anything into them, natural gas, biogas, hydrogen, ammonia, propane, and they will work. And they're highly resilient. They're near zero emissions, so I could permit them anywhere. And they're a very easy installation. They're UL listed and tested, and with grid tie inverters. And so this is a data center that was built, and you could see them. I call them in the zipper pattern. You could see them all down here, and you could even see that there is some gas storage on site. And so why the linear generators? Well, they're 2 times cheaper, less expensive than fuel cells, and they're available in weeks, not months. And so that's a big one for me, right? Because traditional generators are in years now, not even in months. These are much easier to permit in a pinch. I could tell you that I personally have built out 4, 5, 6, 7, up to 11 megawatts of using solid state fuel cells before the utility could even build a 2-year project, 3-year project to build a substation at 40, 50 megawatts. I could get a fraction of the power in on the ground with linear generators and or solid state fuel cells in months because the permitting is easier and they're available. And so here's what you're seeing, by the way. The other reason why I like this, these are software controlled, and they're easy to change between fuel sites, and they're fast response. So I could actually use them as prime power application. That's exactly what I'm doing there. And so, by the way, there's 2 of those cores in each of the in each of the linear generators. These are by Mainspring Energy, I think the best manufacturer of them. And so, what is it? They're high efficiency because they direct convert linear motion into electricity. You could see the reaction zone there, and it's non-flame or burning. And so it's got ultra low emissions in there. And like I said, it's fuel flexible, and it's software controlled. And so I can make any power out of it, unlike in the solid state fuel cells, which are a little bit more difficult when I have a load moving scenario. So these are very high reliability for very low maintenance. In fact, there's only 2 moving parts in the whole thing. And so the cooling design is let's go another way. And so I could achieve very low operation. Again, I can operate these. This is from XCool, who was at the show as well. And we can do these up to about 50 kilowatts per rack easily in this environment. And what I love about this, it's got multiple cooling modes all baked into one box. And I just need to be able to parallel for the level of redundancy that I want to operate in them. And so why the iDeck? Well, I like the iDeck because it checks the boxes against chilled water, direct air, and pump refrigerant. It's low amounts of points. It's simple from a complexity standpoint. I'm only using partial mechanical cooling in order to achieve that. It's very low water and usage. And it has a very fast restart time, and the potential for contaminants is none. It's non-existent because I'm actually not introducing anything inside of the environment. Everything is external to the building. And so here's an example of a 1 megawatt in all of the major operating cities of the world compared to a chilled water operation. You'd see across the cities, it's a fraction of the operation of a chilled water solution. And from a capital cost standpoint, once you consider all of the things with a free cooling chiller system versus an iDeck, you'll notice that I'm less than 70% of the cost of a system. And so from an operating cost there standpoint, it's about 21% savings on operating. And that's, by the way, if you look at the blue area down here, the microgrid, that's including the cost of the PPA and the gas. And you can see there is still a little bit electric. These were modeled based on a fuel cell, not actually a linear generator, but a linear generator is even less expensive. And so has it been used? Well, partially. This is what I could tell you about this. This is the federal government. This is Lawrence Livermore Net Lab, the DICE project, to which PTS is designed and building right now in California for the DOE, the Department of Energy. If you've heard about fusion reaction, again, maybe one of the potential futures of power. This is going to be the lab that will actually do all of the modeling for that, what's known as the ignition lab. And the only one slide that was approved for showing is indeed this one, which is the CFD analysis showing that the racks could be cooled at load. This is just one of the many slides showing at a 6-foot elevation where the heat is contained and it's rejecting. Yes, these are air conditioners going back. They are external to the building, and they are not exactly what you saw in the other picture, but the same concept, different manufacturer. This is one that we had built prior. This is Sandia National Labs on that same campus, actually not too far away from there, but it was one of the larger petaflop systems built that year, and it uses a similar approach. I just showed this because I just thought this was really cool. We did this as a study for somebody. This was actually using immersion cooling, but immersion cooling and or any of the other liquid cooling give off the heat that they give off of the air conditioners on the inside is the exact heat that you need for a grow room. So here in working with the architectural firm that came up with the concept, that heat was being used as a grow room, and that's a linear farm surrounding the data center. And then if you put this big glass bubble over the whole thing, we were trying to present as an economic development where this could be part of the downtown of a city, and you could actually have the data center, perhaps heat capture could be used for, that grow facility, or it could be used for direct cooling, direct water for the entire campus and or city. There's lots of use cases when you're going to put this down. I just thought it was a really cool approach. So look, we're coming to the end. And so the benefit I think here is that it's a true dual fuel source, and that has a superior availability. It's about a 10 megawatt, 10 million per megawatt. For, I'd argue, a true tier 4 approach to this, because you're using 2 fuel sources. It will even cost less for tier 2. I would argue you don't even really need the UPS if you trust that the fuel sources can switch economically between the two, and they can, switch between the Sabima curve. And it's got a 30% lower OpEx and that's including all the fuel costs and the PPA. Remember, with a linear generator and a fuel cell, you wouldn't purchase these as CapExes. You purchase them as an OpEx on a PPA instrument. Just like in the same way you would never pay for your electric utility in bulk, you pay for it monthly. This would work the same way. Ultimately, the design, it's faster to design, faster to build, it's easier to operate. It's a 20% smaller footprint, and it could be deployed anywhere where you can get that limited power. And so thank you very much. I appreciate your time. These are other, you can download my QR code if you want to get in touch with me. Look, I'm deep into lots of other technologies. You could find me on LinkedIn. And so there's lots of areas that I'm involved in across all the technologies, from blockchain and cryptocurrencies. I own hedge funds, as well as all the PTS operating companies and designing build data centers. So hopefully you found that useful. Thank you for your time, and reach out to me if I can ever help you with anything. Thanks very much.